Section 2.6 is called related rates. Related rates takes what we did in the last section, implicit differentiation, and it actually shows how it's used in finding rates that are related to one another. Okay, so this is the application of what the last section was for. So there are some guidelines for solving related rates problems. The first one is, often a sketch is helpful. And maybe often isn't even a strong enough word, like most of the time. Yes?
Is it optional or required?
It's going to be almost impossible to do things without it. So I think you're going to find more often than not that you're going to have to draw it simply to make sense of the problem. So I don't want to say that it's required in the sense that you have to do it in order to always do a problem like this, but more often than not, it's going to be something you're going to want to do.
Okay, I just assumed my teacher has to take off for not drawing.
They would take off, and there are cases where I do that as well. But if I expect it to be drawn, I'll explicitly say it in the directions so that you'll know. Yeah. Second step is to set up an equation that relates the related quantities, the relevant quantities. So if the relative quantities relate with the Pythagorean theorem, you might be setting up Pythagorean theorem. If it relates with a sine, cosine, tangent kind of function, you might be setting that up. If it relates with the volume of a sphere, we're going to have one of those, I think, you're going to set up that. So whatever the equation is that relates the quantities in your picture together, that's the equation you set up. To your question?
No, I was just drawing the relativity.
Oh, okay. And then you're going to differentiate implicitly. The catch is this. Your implicit differentiation will not be with respect to x or y. We did the last section was all with respect to x differentiation, right? Your implicit differentiation with respect to time. How something's changing with respect to time. So it's going to look a little bit different than we did in the last section. And then you're going to substitute in all values that you know and solve for what it is that you don't know, whatever the rate is that you're trying to find. Okay, do you guys have these jotted down? All the holes filled in your notes? Excellent. Here's a question. We have a fish. A fish is reeled in at a rate of 1 foot per second from a point 10 feet above the water. At what rate is the angle of elevation theta between the line and the water changing when there is a total of 25 feet of line from the end of the rod to the water? And if you have a picture in your mind very clearly of where all those quantities are, you're doing way better than I am. So do you guys see what I'm talking about when I say the picture's just almost like required? Right? Okay, so we've got a fish being reeled in. So we got somebody up here at the top, and I don't draw very well, but here he is. He's got a fishing line, and that dot is his fishing line. I know it's not even touching his hand, but pretend like it is, okay? And the fishing line is actually, so if you think about when you throw out a fishing line, it goes out at an angle from you to the water. So he's got his fishing line out here that's making pretty much a straight line. I mean, if he's pulling in the fish, it is taut. That means it's tight and it's straight. You've got your water down below. I should definitely draw water in because I can do that. Watch this. There's water.
Ooh,
See? Fancy. It says that the fish is 10 feet, or he's being pulled in at a rate of 1 foot per second. Let me actually do this first. So this rate is 1 foot per second, and it's negative. Why would I put a negative on that? Yeah, it's getting less every time, right? So it's actually being pulled in, so the fishing line is becoming less, the length of the fishing line. He says 10 feet above the water. So he's like on a boat or on a dock or on the shore, something like that. That's where and he's got a height anyway, right? Because if you hold a fishing line and you're 6 foot tall, then the fishing line's at least, 3 or 4 feet off the ground already. So there's some of that too. So here's our 10 feet. And that part's not changing. I mean, he's not shrinking. He's not doing this, right? He's not going like this with the fishing line. We're not doing that. He's standing still. So that 10 foot is a stationary value. It's not going to change. As the fish comes in, it's still 10 feet. It says, at what rate is the angle of elevation, theta, between the line and the water? So it described an angle, and it referenced the line of the fishing line and the water as the angle. So this is the theta that it's referencing. When there is a total of 25 feet of line from the end of the rod to the water. So they're telling you that at some specific point of time, this is going to be 25. Is it always 25?
No.
No. It's just going to be at one point in time. The length of fishing line is constantly changing as the guy's reeling in the fish, right? And that angle of elevation is also changing, yeah? Because as this line comes in, what's going to happen is it's going to be like right here. And then it's going to be like right here. And eventually he's going to get it pretty much like right below the boat or the whatever he's standing on before he actually pulls it out of the water. So this angle of elevation, as the fishing line moves in, the angle of elevation is getting larger. Does everybody see that okay? Picture-wise? I know there's a lot of context here, and if you don't fish, then you might be like, why would I care about this problem? This one we get. Fantastic. I'm glad I hit you there. It's something that works. All right. All right. What we want to know, though, is we want to know the things that I've marked in my diagram, how are they related? So I've got this length of this triangle. I've got this length of this triangle, and I've got this angle. Those three quantities are related with something from trig. What are they related with? Is it cosine or is it sine? It's sine. The sine function. Do you guys remember SOHCAHTOA?
Yes.
Oh, I'm glad.
All the time.
All the time. Okay, SOHCAHTOA says that if I take this angle, there's relationships between sine, cosine, and tangent in the three sides of the triangle, correct? So we've got to identify from this angle if this is the opposite, adjacent, or hypotenuse side of the triangle. The 10 feet is the opposite. This is the opposite side. And then this long piece right here is the hypotenuse of the right triangle, correct? Okay, so this is sine because it's opposite over hypotenuse. So the relationship among all of this is that the sine of theta is equal to the opposite, which is a 10. It's not ever changing, over, well, eventually it's going to be over 25, but it's not always 25, right? So we need a variable name for the long piece of my triangle. What would you like to use?
Delta X.
X, H, I heard X first, so I'm going to go with X. Okay? Whatever length you use, X or H for hypotenuse, or C for the A squared plus B squared equals C squared, whatever you like, okay? So you've got a side length over there. This is the relevant equation. So if you look at, like, this is like the part 1, draw the picture. This is part 2, create the relevant equation. All right? We're on part 3, which says to differentiate implicitly with respect to time. What does that mean? Well, everything is going to be d, whatever the variable is, dt. So I'm going to get a d theta dt in here, and I'm also going to get a dx dt, because those are the two variables that I've got in my particular picture, thetas and x's. Okay? So let's go through it slowly. We're starting with sine. What's the derivative of sine? Cosine. And theta is the angle, and that never changes. It's cosine of theta. But theta is a quantity that's changing with respect to time, so the derivative of theta is
1.
d theta dt.
Oh, wait.
It'd be 1 d theta dt.
Are we treating it as a variable?
Yes, theta is a variable because it's changing. That's what variable is going to mean. And x is going to be a variable because it's also changing. Do you have a question, Chad?
I was just wondering, how do we know that finding the derivative of all this is going to come out to our real finding answer?
Derivatives are rates of change. It's just how quickly something's changing. That's what it really means. So when you're talking about like speed of cars, that's actually a derivative at any specific point in time as well. So it's actually just what the word derivative is what we mean by the change of what's going on. Okay? Okay, this is the left-hand side. Are there any questions on why sine of theta became cosine theta d theta dt? Okay, on the right-hand side, instead of leaving this written like this, I would prefer to write it like that. Are you guys okay with that? Because really, it's sort of like, looks like a quotient rule, but it's not really. It's a constant 10 on top. It's not a very exciting quotient rule. Can you do it as a quotient rule? Yes, you could. But I'd rather do it as a chain rule because to me it looks more like a chain rule. If you want to do it as a quotient rule, it'll be okay. So if we do it as 10x to the negative 1, what do I get as the derivative of 10x to the negative 1?
Negative 2, dx, dy.
Okay, so this is the overall first piece that we've known and loved now for about 3 weeks, right? Maybe not quite 3 weeks, but we're getting close to that. Negative 10x to the negative 2. But we're doing this with respect to time. That variable x is changing with respect to time. So whenever I take its derivative, I'm going to get a dx dt as well. It's how it's changing with respect to time.
This is part 3 also, right?
Yes, we're working on part 3 right now of your sort of 5-step process or whatever I called it before. Yes, exactly. And I want to clean it up just a little bit. So this is cosine of theta, d theta dt equals negative 10 over x squared dx dt. Is everybody good so far? So good, mostly? So good so far? Okay. Step 4 says to substitute in known values.
So we know the XTT.
Okay, so where will the 25 go?
dx
Not quite. It'll go to, what'd you say? X. 25 is x, okay? Because x is the length of the line, and the length of the line is the 25. Yeah, at the 25 length. So this is 25 squared. There's one other value that's written on my screen at the moment that needs to go somewhere. Yeah, the dx dt, how that's changing, right? Negative 1.
Oh, is that a mouse? Oh, yeah.
So it's not labeled right now, but we could go back here and label it. This is dx dt. Now we're supposed to be solving for d theta dt, so it's certainly reasonable that I don't know that quantity. That's what I'm supposed to be finding. But right now on my screen, I don't have written down at all what is theta. And we know theta is changing.
That's what we're trying to find.
We're not trying to find theta. We're trying to find d theta dt, right? The the rate of elevation. At what rate is the angle of elevation changing? So right here is the piece we're trying to find.
Can't you find theta if you inverse?
Yes. We have enough information that at this specific point in time, when x is 25, we have a triangle with one side 10 and a hypotenuse of 25, right? So if I have the side of the triangle, this is the picture I've got, drawn sloppy now, 10 here, 25 here, and theta here, and we were told, we actually created it just a moment ago, that sine of theta equals 10 over 25, right? Can I find theta?
Yes.
Absolutely can. How do I do that? Inverse sine. So you take the inverse sine, and it's in your calculator. Make sure that you're still working in radians. You didn't go changing it back to degrees for some other class, okay? Inverse sine of 10 over 25. And when we get this, it's going to be probably an ugly decimal, and we want to keep a lot of those decimal places.
Wait, do I have to change it to degrees?
No, no degrees. Everything in radians. Always, always, always in radians for calculus. We want to be in radians. We'll leave it in the 0.411, whatever it said. Is that your question, Bryson? Yeah. Yeah, we're going to leave everything in radians for calculus for always. Always and forever. Okay, you said it was 0.4 something. What was it, Luke?
0.4115.
Let's get 6 decimals just for fun. 411 516 516 or 7. Probably not a big deal either way. Okay, this is our angle measure that we're going to use back in the problem then, okay? So over here, I have the cosine, and I'll show you one other way you could do this, of theta, and the theta y'all just found me was 0.411517, like that. So, can I solve for d theta dt now? Yes, I can. I definitely need a little bit more space. Let me do that. Okay, so on the left-hand side, I have d theta dt. On the right-hand side, I have 10 over 625, I believe.
Yep.
And then I have all of that you're going to divide by the cosine of 0.411517. When you get this, you're going to get a decimal answer. We'll go with just, looks like I've got 4 decimal places written down here. I don't know why. Just whatever the problem tells you to use that. What do we get when we divide 10 divided by 25, and then divide that by the cosine of 0.411517.
What is 436? Is that wrong?
Yeah, it is. Try again.
I'm wrong.
It's okay.
I got 0.017.
I got point
Okay, that
zero
sounds
seven
closer.
seven.
Point
Point
oh
zero
one seven. Give me one more
seven.
decimal.
Four,
and then-
five, round
Five?
it up.
Okay. And anytime we're dealing with application problems, we need units on them. And here's the cool thing. Because we've written this as d theta dt, we can actually look at that notation to get the units. So what are the units on theta? Radians. What are the units on time in this problem? It was seconds. So this is radians per second. Now, I am perfectly fine with the way we found theta, but I do want to show you one other option on finding how theta can be found using theta. Now, we needed to find theta so that we could take the cosine of it, correct? But take a look at this picture up here as we drew it. If you think about the picture drawn here, what's the cosine of theta in this picture? How do you find cosine?
X over 25.
Okay, so the piece
Well,
that's missing,
well,
right?
or X
Okay, so we don't have
A
it
or
called,
something.
how about we call it A? All right, so if we had this side right here called A, then the cosine of theta would be the A over the 25, right? Could I find A?
Yes.
Yeah, how could I do it?
Pythagorean.
Pythagorean theorem. So we could actually, instead of finding what the angle theta equals, I could find the missing side of my triangle, whatever that value is, and write that value over the 25. And then instead of plugging in theta as the 0.411 number we got, we could replace all of cosine of theta with the A value over 25. There's nothing any better about it. It's just a different way of processing the same problem. Okay? Are we good with that one? Sure.
We always want us to round our decimals.
You'll have to round them at some point because application problems never work out. True application problems never work out to nice, pretty numbers,
Yeah.
right? So you're going to have to round them somehow. We're going to go with 4 decimals, okay, on like homeworks and stuff like that. And I'll remind you when we get to a test. It'll tell you in the directions. I'm not trying to trick you up on like how many decimals does she want. That's not the point, okay? WebAssign should do the same thing, tell you how many decimals it wants. If it doesn't, then as soon as you get an error, you can probably look at it and try and figure out if it's an error in the number of decimals. So, but usually does a pretty good job at telling you the decimal places. Chad?
Where'd you say the radians came from? Where's it the radians per second?
Because this is the angle measure of d theta over dt. So the angle measure theta is measured in radians. Okay.
Just because that was, just because.
It's because we always measure angles in radians in calculus. So anytime you see an angle theta, you're always measuring it in radians. The calculus rules that you know and love now, right, is all based on radian measurements, not on degree measurements.
Okay.
Yeah. Okay.
Gotcha.
All right, we're going to at least draw the picture for this one, and then we can stop, okay? A spherical balloon is inflated with gas at a rate of 800 cubic centimeters per minute. How fast is the radius of the balloon increasing when the radius is 30 centimeters? So what is the picture I'm going to draw? Better than a circle.
I'm a hot air balloon.
A sphere, right? Yeah, so it looks something like this. I'm drawing it so you guys can see. You draw the circle and you draw this sort of arc right here, and then you draw the back arc where it's dotted, and then you've got a sphere. That's how you draw a sphere. That's a 3D picture I can draw pretty well.
3 sphere.
All right.
Oh, yeah. Our math meeting.
Okay, are we good with the picture from the meeting the other day? Had to miss it, yeah. All right. A spherical balloon is inflated with gas at a rate of 800 cubic centimeters per minute. All right, so what is the measurement of this sphere that we should label? There's something in this picture we should probably put in there.
Radius.
The radius. The radius is an important feature when we're dealing with spheres or circles. So this radius R needs to be labeled in here. And they tell us eventually that R is going to be 30, but that's again kind of like my 25 in the last problem, right? It's at a specific point in time. It is going to be changing. Okay. What else do they tell me? It says that the rate of gas is being inflated, so it's getting larger, right? We're blowing the balloon up at a rate of 800 cubic centimeters per minute.
Yeah, but your question-
What is 800 cubic centimeters per minute measuring? Volume, right, or at least the change in volume, right? Cubic centimeters per minute. This is a rate of volume. Cubic measurements are volume rates. So this is actually dV dt, because it's how the volume is changing. It's increasing. Right? Volume is how much space the object takes up in 3 dimensions. So there's only one equation that I'm going to need to have for this. And what would the equation be? Volume. Because I have a related rate, the volume, right, dV dt, that's relating this. So what would the equation be, or do you remember what the equation is for the volume
Pi r squared cubed.
Square?
Yeah, cube.
cubed? Good memories.
R. We were at the R.
Oh, pi, I left my r out.
Yeah, we know.
Thank you.
Can't believe I'm-
Pi r cubed. 4/3 pi r cubed.
That's it.
That is the volume of a sphere.
Are we gonna get ones on the test like this where we have to?
They won't be
remember
one,
weird formulas
either,
like that?
either it'll be one where I would expect that you would know the formula, like the triangle, sine, cosine, tangent, you should know those. Pythagorean theorem, you should know them, okay? It'll be something that you see frequently in your mathematics stuff. Or if I put something like, we're gonna do this one's a sphere, the next one's actually a cylinder. If I did something that was more like you just don't use it every day, I'd give you the formula for it, okay?
Like that?
Yeah, like this one, 4/3 pi r cubed. All right, we have time still to take the derivative, I think, on this one, don't
Okay.
we? All right, what's the derivative of 4/3? Well, what's the derivative of the left-hand side? What's the derivative of v?
dV dt.
That's dv dt.
4/3.
I have a 4/3.
3 r squared.
Okay, I have a pi as well, right?
Pi.
The 4/3 and the pi are numbers.
Yes.
I know pi doesn't look like a number, but it is. What's that?
You do power rule.
Yeah, and then you do the power rule with r cubed, so
3R squared.
3r squared.
But we know r though. Do we still have to find dr dt?
PR dt.
Okay,
We still do.
yeah, so r is changing. We do know r, but we only know it at a specific point in time.
Okay.
Not all the time. It is changing. So we do have to take the derivative of it. It is 3r squared, and then in dr dt.
So we still
Okay.
find-
So this was step 1. This was step 2. This is step 3. You guys are going so fast, we're going to finish the problem. Okay? Which pieces of this do you know?
3 to the 2/3 we have.
You can. And in fact, if you'd like to, we can do that real quick before we substitute anything in. So dv dt is 4 pi r squared dr dt. Does anybody happen to recognize 4 pi r squared formula, what it is?
It's like
It's the
yeah.
it's the surface area of a sphere. And that's actually not a coincidence. When you take the derivative of volume, you get surface area. Isn't that cool? Yeah, fun stuff. All right, there are 3 variables here. Do we know 2 of them?
Yes.
We do. Which 2 do we know? dv dt, what was that one?
800.
That one was 800. Here's my 4 pi, and we know r. R is 30. So can I solve for dr dt? Absolutely. We would need to take our 800. 30 squared would be 900. 900 times 4 is 3600. Pi.
Can we multiply the pi or do you want us to leave it?
Yeah, can we just leave the pie?
Most of the time, when you're doing an application problem, like if somebody asks you how far is it from Shawnee to Midwest City, and you tell them the answer and it's got a pi involved, they're going to look at you like you just, or if you gave them an answer in a fraction, right? It just isn't going to make sense in terms of the context of the problem. Decimals are better. What's that?
So 2 over 9.
Yeah, probably not what you're looking for. We don't want the pi
I
involved.
like multiplying out.
Okay, so if the directions in WebAssign tell you to keep it in pi, then by all means do that, but most of the time we're going to simplify. So
What
this
are the
is,
units? Yes.
I'll show you in a second.
Yes, ma'am.
All right, so I did cancel my 2 zeros. So if I do 8 divided by 36 pi, you probably want to make sure your 36 pi is in parentheses in your calculator. You don't want your calculator to think that you want to do 8 divided by 36 and then times pi. Hmm?
3,600.
It is, but it's also 800 on top.
Okay, so you're
So,
using-
yeah, I simplified the zeros out because I divided them by 100. So, yeah. If you don't, it'll calculate, it'll do it for you. What do you get for DRDT?
Yeah, 0.071.
Yeah, 0707.
0707. And then Mooney asked me about units. What would the units be?
It's units for time.
So you look at the DR and the DT. What are the units on R?
R is centimeters.
Centimeters. And then what are the units on time in this particular problem?
Cubed by
Per
minute.
minute.
Per minute. It's not cubed though. Okay? The units on the radius R is simply centimeters.
Okay.
Okay? The volumes units had centimeters cubed because volume is a cubic measurement. So we get 0.0707 centimeters per minute.
Oh, yeah.